So my name is Ashrut Ambastha. I'm a staff architect at Mellanox, and I'm going to talk about networks. Now, since I think we're running a bit behind, so I'm going to quickly go through the initial parts, and I'm going to introduce something new, which I think you might not have seen from us. First, a couple of bragging slides. Okay, so 2019 HPC top 500 list. Actually, Mellanox now was listed as the company which powered the backbone for number 1, number 2, number 3, 5, 8, and number 10 system out there in the top 500 list. Now, these are systems which are the DOE systems, ranging from around 9,000 InfiniBand nodes. The Chinese system is around 41,000 InfiniBand nodes, and then it also encompasses AI systems. I will talk a bit about those. So since this conference is all about the convergence of HPC, AI, and cloud, so I've kept the theme of this talk related to that. So just one more slide on the top 500. This year's latest list also debuted our HDR systems in the list. So TAC with, I think, around 8,000 HDR InfiniBand nodes with a factory topology was number 5 in there. And then we had Mississippi State, CSC in Europe, and also University of Tsukuba in Japan, all of them utilizing HDR InfiniBand interconnect. Now, some of them are running multi-rail, some of them are running HDR at 200 gigs, and usually most of them are HDR 100. Due to PCI limitations on the motherboard side. But now we have native HDR support with one of the AMD platforms. The ROM processor basically contains a PCI Gen 4 interface, so you can, with a single slot, take out 200 Gbps. So with that, just have a look at the evolution of interconnect speeds and feeds. If you look at this slide, all the old timers would say, yes, Cray started off with the crossbar, and round about 1999, Mellanox started off with InfiniBand. At the same time, we had the Quadrex QSNet, we had MyriNet. The QSNet got bought by Nodal, where they made it with, they put a gateway to Ethernet from there. Of course, everybody knows the QLogic part of InfiniBand, wherein the InfiniPath got changed to TrueScale, and then that was acquired by Intel, which basically became OmniPath. I think right now we are at, I'm not very sure about the roadmap on OmniPath over there. Cray has been there with the C-Star, Gemini, Aries, and recently now we've been announcing the Slingshot Interconnect. And last but not least, InfiniBand, we've been going pretty good from SDR, DDR, all the ERs, right now HDR, and we have a strong roadmap towards NDR InfiniBand and then XDR. NDR is in the definitions, and also people at Mellanox are already working on the ASICs for that. It will be 400 gig per port kind of bandwidth. What I want to highlight from this slide is, if you can see, the color of the bottom arrow is completely blue. What it means is that being standards driven, this technology allows you to be forwards and backwards compatible. So if you as a institution started off with a QDR or an FDR deployment, and now you upgraded some portion to EDR, and let's say now you want to connect a very large HDR machine, but still want to use the storage from the previous generations, you can actually natively mount it to your new HDR cluster, instead of going through routers or kind of a protocol converter, as I would say. You can natively mount and use all your previous systems. Of course, you would not want to run an MPI job between various generations, because then the performance will suck, right? So that's what I wanted to highlight from this slide. But it's not just speeds and feeds that we have been talking about. There needs to be intelligence in the network. I remember I have talked about various compute engines that we're trying to place in the network. So we're trying to innovate in all the verticals inside the high performance interconnect. On the layer 1, if you look at something called Shield, which refers to our self-healing network technologies, wherein if there are the switches are capable of recognizing failure in advance on layer 1 and then alerting or even calculating routes, alternate routes, right? So you heard a lot of people talk about GPU Direct. Professor Panda talked about GPU RDMA capabilities where you avoid multiple copies in your system memory and get higher performance. Everybody knows about the offloaded hardware technology, hardware RDMA technology that we bring in. And there are a lot of transport offloads. There are, in the communication framework, there are a lot of offloads that we have brought in. And I will explain one of them in this presentation. And now we're also bringing in configurable logic into the network, programmable logic into the network, which gives a whole new dimension of trying to combine pure HPC cluster with a cloud framework or an AI workload. All that can be now integrated. So let me quickly talk about some of the, or maybe one detail on the in-network computing technology that we bring in. We do a lot of GPU Direct. I talked about Shield. I talked about. I'll like to describe more in details the SHARP protocol. So the philosophy at Mellanox right now is operations which should be done closer to the network should be done in the network, rather than doing those operations inside your compute cores as a C code. And only then we will achieve the scale of exaflops that we are looking at now. Okay? What do I mean by, so I'll try to simplify this. What do I mean by this? It's a nice marketing name, Scalable SHARP, Hierarchical Aggregation and Reduction Protocol. What does it do exactly? So let me give you an example of MPI Allreduce. Okay? What is a reduction operation? So there are a lot of MPI collectives. You have point-to-point MPI. So every time when you are solving any problem, you will have a partial differential equation mostly. You will break it down into a sparse matrix or a matrix vector multiplication. And then the matrices are distributed among servers. They'll all compute their part. And then they will collate the data and give it to a source. And then the new iteration will start off, right? So for collating the data and redistributing, these are all collective operations. So MPI reduce is a collective operation. It can be as simple as taking an average. So let's say you have a 4,000 node job. One of them during a collective operation will be designated as a master node. Okay? And all of these guys will do their part. They'll calculate their result. And they need to send it out to the master processee. The master processee is going to receive data from everybody, then do some reduction operation, which can be MPI sum, MPI average, and then it is going to redistribute the result to everybody else. That is what is Allreduce, when you redistribute it to everybody else, right? Now, you can see that there is a bottleneck. If you do it in software, for example, this reduction is running inside this master node, then it has to take everybody's result one by one. And then only it's an incast scenario. Even by software, if you have done some optimization and let's say spawned multiple masters across all these switches, still one of them will have to gather from everybody else and then send it across and then send it to the master. Master will do the final operation. So what we said, why not use these network elements as some sort of a compute engine as well? And that's what we introduced inside all our neo generation InfiniBand switches, wherein this switch, the node, the leaf level switch, will get data from all of the guys directly connected to it and do the reduction operation. Therefore, now you can see that all the leaf switches can do their part in parallel. And at the end, they will send out their answer to the master, and master will do the final reduction and do a distribution in the same manner. It is going to distribute to all these guys, and these guys will in turn distribute over here. So now this reduction operation is also being done inside the switch. Now I don't mean that I've put a full-fledged floating point unit inside, but it can do MPI reduce, Allreduce, offload inside the switch. And that reduces the latency of these collectives by multi-folds, almost 8 to 10x, as you can see over here. And usually, these reduction operations are very small operations. If you, for example, take WRF and you do an MPI profiling of WRF, MPI reduce will be a 4-byte reduction, that's it. And this is where these intelligent network units help out. It's not just slideware. I will show you real results from Oak Ridge. So this is on the Coral Summit system. 2000 nodes, MPI all reduced latency for a 2 kilobyte message size. If you take IBM Spectrum MPI, and this, by the way, this is an IBM system, so we are comparing against IBM Spectrum MPI and standard Open MPI versus Sharp-enabled MPI, which is part of the HPC-X package. And here you can see there is a decent amount of all-reduce performance boost in the collectives. So I just gave an example of Allreduce. The same thing holds true for other collectives, Barrier, for example, as well. Okay? Some more data. It does not work only on standard tree architecture. So if you go into this slide, you will say, okay, if you have a hierarchical tree, then only this collection can be logarithmic. Otherwise, how does it work in a mesh? So in a mesh architecture like a Dragonfly as well, we can reduce this into multiple subtrees and then run Sharp on it. And therefore, this is example from 1500 nodes, 60,000 MPI ranks, Dragonfly topologies, running Sharp versus standard software MPI. And you can see even as you keep scaling or you increase your number of reduction message size, your latency is again almost 2.5 to 4x less compared to standard software MPI. So this is one thing that we have brought into our high performance interconnect. So the interconnect is not just about speeds and feeds and lower latency. It's also about offloading as much as possible. Now, guess what? The same thing holds true for AI workloads as well. Think about a standard, image recognition kind of workload. Now, if you have model parallelism, it is slightly difficult to use this. But if you have data parallelism, then what do? You distribute various, training data sets amongst multiple target nodes. Okay, and then all the target nodes, they operate in their subset of images. And they calculate a delta. When you're doing image recognition, for training purposes, you calculate a delta in the weights, right? When you do the difference. Now, all of them calculate their delta and then send it out to a master server or a group of master server, which is called the parameter server. The parameter server compares it against its function and calculates the new weight and sends it back to all the target nodes, who again do an iteration and calculate the new delta. So this is exactly like the reduction operation I talked about. And therefore, these technologies that we bring into the switch works very well for machine learning workloads as well. We are working on adding these functionalities onto the standard frameworks like TensorFlow, like Caffe, and therefore, you're expected to see better performance. We do have real system performance like RasNet 50 using Nickel 2 without Sharp and with Sharp. These are initial results, but we still see at least 15 to 20% kind of improvement in machine learning workloads as well. Even without Sharp, if you look at AI systems, the ImageNet training record breakers are Facebook, Preferred Networks, and Sony. And all of these are based on EDR or FDR InfiniBand network. Even NVIDIA's internal DGX Saturn V system with 124 DGX boxes is based on EDR InfiniBand technology. The DGX2 platform contains, I think, 8 rails of 100 gig InfiniBand. Now again, there is NVLink. We talk about NVLink. NVLink is not a fabric topology. I mean, you may extend it, but it's mostly within the framework of a box. Okay? When you have to go into 1,000 nodes of GPUs, or let's say even 200 nodes of GPUs, you need to have a fabric which connects them. And that's where the InfiniBand GPU RDMA enabled interconnect comes into picture. So some numbers from these systems as well. you have GPU scaling efficiencies between FDR and EDR. Again, you can see a large gap here. It's not just because of the interconnect, it's also because of the fact that the system with EDR contains a Volta GPU, whereas this one was Pascal, even though the number of GPUs were same. But the faster you go, the better interconnect you would need. And I'll give you simple math here. So you're doing teraflops, right? And teraflops, even if you're doing metrics into vector multiplication, you will have ON cube kind of calculations. That means if you put in n data points, you will be able to do n cube operations on it. Now, as this n cube is basically nothing but your teraflops, right? If you increase your teraflops, you need to give it operands, right? Unless and until you give those operands, you will not be able to churn out those teraflops. That's the reason why you need to have a balance of compute to communication ratio. We call it in terms of gigabytes per second per teraflop or vice versa. So you need to have a thicker pipe, and that's why most of the fat node systems have a multi-rail InfiniBand or would go with a higher bandwidth, 200 Gbps kind of InfiniBand technology. So with that, let me quickly finish my first portion, which is the majority. I also want to talk about this. We had our colleagues from Cray talk about various benchmarks, and I agree with them that point-to-point OSU benchmarks are not relevant. If you're looking at a cluster and if you just say, okay, give me OSU MPI bandwidth and latency number, it's not relevant. What you need to look at is loaded performance, loaded latencies. And I'll give you one example benchmark which ORNL Oak Ridge people ran. It's called MPI graph. And let me define this benchmark. So consider you have a 10,000 node cluster. Now what you do is divide it into two subsets of 5,000 node each, okay? And now do random permutation of source destination pairing and run MPI ping pong or bandwidth simultaneously, okay? You will get between every pair, you will get some bandwidth numbers, right? Now you change this random permutation and you'd repeat it multiple times. And then you take an average of what is the maximum bandwidth you got, and this is what you get. If you have a nicely balanced system, you will get, for every permutation, you will get near about line rate. The percentage over here represents the line rate of your injection bandwidth. So if your bisection versus injection is 1:1, you should get, if it is a 100 gig network, you should get 100 Gbps for all the nodes, right? You will get it only and only if you have a full crossbar. Like if you have a system which has an imaginary switch which is 100% non-blocking full crossbar, then you will get 100. You will get a delta function at 1 at 100% over here. That means every communicating pair got its 100 Gbps, but that does not happen in real systems. What happens is, depending on your topology, depending on what kind of routing is used, there will be some systems which will be sharing some network segments in the topology, and those systems will not get 100%. They will get maybe 50 Gbps because they shared it with somebody else. Some of them will get lower than this. So adaptive routing was something that existed in Mellanox's interconnect right down from QDR days. We never enabled it in software, it was there present in hardware. But now with the newer HDR and even EDR InfiniBand architectures, we have fully functional adaptive routing because now that's the need of the hour. We have applications which scale a lot, which do lots of all-to-all. So if you're doing WRF, you'll only communicate to the nearest neighbor and the fourth nearest neighbor. If you do an MPI profiling, you will see that. But if you're solving anything in the Fourier domain, you will do an FFT, which results in a matrix transpose. When you do a transpose, you have to do all-to-all for every iteration. When you do all-to-all, you will always be bound by the slowest person over there. Okay? And that's where adaptive routing on this big supercomputer enables almost 100% network utilization. So if you're looking at benchmarks, look at something like this. Look at MPI graph performance of your entire cluster rather than looking at just point-to-point operation. Look at the collectives latencies. That's what I would like to say. There are many other things. Congestion control on InfiniBand has been there for quite some time. Our first stint with congestion management was way back in 2010. Interest of time, I would not go into the details, but anybody wants to talk with me offline on the various congestion management and quality of service capabilities of IB, we can discuss it offline. Let me come to the second part, which may be more interesting to people who are looking at building HPC clouds. So this portion is for the cloud enthusiast. Now, again, it has been around for quite a while. I mean, if you go to OpenStack website, there will be cookbooks on how to do InfiniBand plus Mellanox with Neutron plugin. This is for the Pike release. You will find it as early as the Mitaka release of OpenStack on OpenStack website. You will also find, recipes on running, we run it over containers. Actually, I don't need to show this because many of the people over here talked about running, containers with InfiniBand. And the fact that, it's pretty easy for us to do. I mean, we've got container capability, even over virtualization. This is, I think, recipe for doing Docker with IB. It has been around from ConnectX 3 Pro onwards. So, it just seamlessly carries over. So I will talk about something new that we have. So let's look at this particular adapter. We call it the BlueField. And now, in the era of smart and intelligent NIC, we bring a programmable adapter. What is it exactly? So this one is a product of our acquisition of Tylera, which was around 2 years back. But we integrated in a single ASIC the standard ConnectX subsystems along with 8 ARM cores running at a decently high frequency with lots of accelerators, mostly on the security side of things because it is also meant for secure clouds, and a PCI Gen 4 switch. So this chip can be programmed to work as a storage target controller. It can be programmed to run as a standard InfiniBand RDMA capable adapter. You don't have to program it. It inherently runs that. And it can be programmed, or not even programmed, it's got hardware engines inside to do IPsec TLS offload at line rate. We can give you 200 Gbps TLS on this. Now, it doesn't mean that you use it for your HPC MPI jobs. It has a different purpose, and I will talk where it is more suited. Have a look at this kind of architecture. Let's say you're deploying an HPC system where it's a big cluster. Maybe you've constructed using a standard ClossNet architecture or a Dragonfly with multiple groups. Let's suppose you want to have a certain set of this system, maybe 20%, which should be cloud ready, or it should be able to run HPC workload, and it also is capable of to be configured using standard OpenStack Neutron controller, but you want to give a bare metal to all your users. So here there's a nice isolation line. This is basically your NIC. This entire thing is your NIC, and this is your entire bare metal host. So what we do is we run on the NIC your control plane. We run on the NIC in the ARM processor, let's say the Neutron plugin, where you have any SDN controller. By the way, the NIC has got an out-of-band 1 gig management port. So you have, let's say, a 1,000 node cluster with these NICs on it, okay? And the NIC provides a SRIOV function to the host directly to the bare metal, or it can provide, a VirtIO interface. If you don't want that kind of performance, it can give you a VirtIO interface to your VMs. It can give interfaces to your container. And even if your users have root access on this entire machine, it is completely isolated from network point of view. So if you want to kind of quickly erase the entire system and give it to another user, all you need to do, the administrator basically just logs into this. And then host access to the SmartNIC can be blocked by the hardware. The only way this SmartNIC can be accessed is through the out-of-band management port, or through other out-of-band capabilities. Even through the NICSI you can actually get onto this, but the entire system is available for you to be provisioned as a bare metal server on your high-performance cloud. And this is how it would look like. This adapter enables SDN in bare metal clouds, where you get the full capability of a HPC interconnect without losing any of the flexibility of the cloud orchestration. Okay? That's not all. We also do something very neat over here. What we do is, let's say you want to have a very fast scratch storage mounted. Nowadays, everybody is looking out for NVMe over fabrics, right? Or for very fast scratch, they also try to put NVMe drives into each and every compute. We say don't do that. Have a big blob of NVMe somewhere out there in the network, which is exposing NVMe over fabrics. What this adapter can do is run an NVMe over fabric to standard NVMe emulation in hardware in the NIC. So one of the physical functions of the NIC card appears as an NVMe drive to your bare metal host. Okay? So if you don't need to have a host with an NVMe over fabric client or a driver for that, because standard NVMe capability has been available in the Linux kernel from quite some time now. So any standard Linux kernel will see the fabric, the drive which is over the fabric, as its own local drive. And since it rides on top of RDMA, you will get performance which is completely equal to the local drive. So the same NIC card, I mean, we talk about integration of storage into the fabric. Here, we're trying to go one step ahead, saying, InfiniBand storage, RDMA-based storage has been existing for quite some time, Lustre, Gluster, GPFS, name it. But now you can have very fast block burst storage directly connected to your systems. Now, we've got NVMe over fabric target and client offload capability on our standard ConnectX adapters as well. What BlueField gives you is that emulation I talked about. So if you have a standard ConnectX, you still need to run NVMe over fabric's driver onto your on your OS. With this, you don't. You can even run hypervisors which do not support NVMe over fabric right now, because that hypervisor sees this NIC card as its own local drive. So with this, I think, okay, I'm exactly on time. I would like to say there's a lot of intelligence that we are brought in, and we continue to innovate on the network side of things. It's not just limited to very traditional only HPC. By only HPC, I mean only scientific HPC, offloading only MPIs or doing some sort of tag matching or doing adaptive routing or congestion management. We also bring in capabilities like Sharp, which I talked about, also bring in capabilities of NVMe over fabrics. There's a lot of things we are adding, erasure coding, which Professor Panda mentioned. There's T10diff, there is RAID capability on the NIC itself. The basic philosophy is, again, network operations, let's leave it to the network processor rather than using some of your Xeon or expensive CPU cores for doing them. And at the end of the day, backwards and future compatible, that is our motto. So when NDR comes in, it will definitely be compatible to EDR as well, and you can keep growing your cluster. Thank you.